In this video, we'll go over what the eigenvalues and the eigenvectors of a matrix are. We'll go over how to find eigenvalues and eigenvectors, and we'll introduce the characteristic equation and characteristic polynomial of a matrix and how those are used to find eigenvalues and eigenvectors. Our examples will include 2x2 and 3x3 matrices. There are chapters in the description if you want to skip around the video. Let's get into it. Beginning with the definition. If A is an n by n matrix, then a non-zero vector x in Rn is called an eigenvector of A if A times x is a scalar multiple of x. That is, ax equals lambda x for some scalar lambda. So this is the key idea. For x to be an eigenvector of A, it must have the unusual property that when multiplied by A, its direction doesn't change, its magnitude is the only thing that changes. In general, multiplying a vector x by a matrix A could transform it in all sorts of ways, usually changing the direction and the magnitude. But an eigenvector has the interesting property that only its magnitude is changed, with also the possibility that it flips direction if the lambda value happens to be negative. Speaking of that scalar lambda is called an eigenvalue of A, and the eigenvector x is said to be an eigenvector of A corresponding to that eigenvalue lambda. So each eigenvalue could give way to many eigenvectors, as we'll see in our examples. Once more, in a nutshell, given an n by n matrix A, if there's a vector x that when multiplied by A is in effect just multiplied by some scalar, that scalar is called the eigenvalue corresponding to the eigenvector x. Quick note about the definition. We require that the eigenvectors are non-zero so that we don't consider the trivial equation a times 0 equals lambda times 0, since this equation would suggest that every real number is an eigenvalue, because any real number lambda would make this equation true. So we don't have 0 eigenvectors. An eigenvector has to be non-zero. Now, what does this whole situation look like? Well, in R squared, it could look like this. So the idea is that we have a vector x, that's our eigenvector, and it's an eigenvector of some matrix A that, when multiplied by x, has the effect of just scaling x by this scalar factor called lambda, which is an eigenvalue. Now, if the eigenvalue is between 0 and 1, it would scale down the eigenvector. It'd be a little bit smaller, but it's still going the same direction. If the eigenvalue is greater than 1, it would stretch it out. You can see that. That's lambda times x. It's going the same direction as the eigenvector x, but it's a bigger vector. On the other hand, if the eigenvalue is negative, between 0 and negative 1, then it's going to reverse the direction, but it's also going to shrink it a little bit. So it still lies on the same line, but it's going the opposite way and is a little smaller. Or if lambda, the eigenvalue, was less than negative 1, it would flip the direction of x and it would make it longer. So there's the eigenvector x, and there is lambda x. It's reverse direction, and it's bigger. And remember, the idea is that all of these stretches we see in these pictures, in theory, resulted from multiplication by a matrix. And it just so happened that multiplying x by that matrix actually just stretched it by some factor lambda. That's the interesting fact that makes x an eigenvector of the matrix A. Multiplying it by A just has the effect of stretching it. Let's try an example. Here we're given a matrix A and a vector x that we are told is an eigenvector. Let's verify that x is an eigenvector of A and find the corresponding eigenvalue. Now, how do we verify that x is an eigenvector of A? Well, by definition, we know that it must be the case that A times x will just equal some scalar multiple of x. That's what it would mean for x to be an eigenvector. So let's calculate A times x and see if indeed it is a scalar multiple of x. Doing the matrix multiplication, we'll have this row matched up with this column, which is going to give us 1 minus 2. And then this row matched up with this column, that's going to give us 3 minus 2. So the resulting matrix, or column vector, is 1 minus 2, which is negative 1, and 3 minus 2, which is positive 1. So yes, this is indeed an eigenvector. What's the corresponding eigenvalue? Well, what would we have to multiply x by to get this product ax? You may notice that it's just -1. If we multiply x by -1, the first entry will match this first entry, and the second entry will match this second entry. So indeed, x is an eigenvector of A. In particular, it's an eigenvector corresponding to the eigenvalue lambda equals -1. Multiplying the vector x by the matrix A has the effect of just reversing x's direction, multiplying it by -1. In that example, finding the eigenvalue of -1 was pretty easy because we were given an eigenvector to work with. But in general, how could we go about finding an eigenvalue? Well, it comes down to this equation, of course, the equation that comes from the definition. When does our matrix A have eigenvalues? When will lambda be an eigenvalue? Well, let's see. Ax would have to equal lambda x, and we could rewrite lambda x as lambda times the identity matrix times x. That way, if we subtract ax from both sides, giving us this equation, we can factor the x out of the difference of the two matrices, and thus we arrive at this equation. Lambda times the identity minus a times the vector x equals 0. If this equation has a non-zero solution, so a non-zero x vector that would satisfy this, then that x would be an eigenvector, and thus lambda would be an eigenvalue. So lambda is an eigenvalue of A if and only if this equation has a non-zero solution for x. Equivalently, we've done this many times, the coefficient matrix would have to have a zero determinant. That would also mean that this homogeneous linear system has a non-trivial or non-zero solution. So go figure, this whole thing comes down to determinants. We really shouldn't be surprised. The determinant of the coefficient matrix would have to equal 0 for this equation to have a non-zero solution, which would mean that lambda is an eigenvalue. Again, lambda is an eigenvalue. If this equation has a non-zero solution, that means the determinant must be 0. That's equivalent. So if the determinant is equal to 0, we get this equation, and this is called the characteristic equation of the matrix A. And if we expand the determinant on the left, we would get this. The identity matrix multiplied by lambda will have zeros everywhere off the diagonal, and we're subtracting the matrix A. So this is going to be the determinant of the matrix whose off-diagonal entries are just the negation of A's entries. On the diagonal, we'll also have the negation of A's diagonal entries, but with a lambda added because of that lambda I. So you can see that. We have the negation of A's entries off the diagonal, but on the diagonal, they all have a positive lambda in front. And this determinant must equal 0 for lambda to be an eigenvalue, because if the determinant is 0, this equation, guaranteed, will have a non-zero solution for x. Let's run these numbers for the example we just did. We found that lambda equals -1 was an eigenvalue of this matrix A. So then, let's look at the characteristic equation. First, we would have this difference, lambda I minus A, which is lambda times the identity minus A. That gets us here, and then we would need to take the determinant of this matrix. That should be 0, and the determinant of the 2 by 2 matrix is straightforward, just -2 times -3, minus -2 times -3. Oh, look, it's 0, just like we would expect. So we see how this eigenvalue of -1 does indeed lead to the relevant determinant being 0. But that's not usually how this goes. Typically, we're going to use the characteristic equation to find the eigenvalues. Let's see how that works. We know that our matrix A has -1 as an eigenvalue, but it actually has another eigenvalue as well. And now that we know the characteristic equation, we can find these eigenvalues. We're going to use the characteristic equation to find the eigenvalues of A. We should find the eigenvalue -1, which we already know, but we'll also find another one. So this is the equation we are considering, the determinant of lambda I minus A. This is set equal to 0. This is lambda times the identity. We are subtracting I So this leads to this matrix here, and we're taking the determinant. This determinant must equal 0. Any lambda value that results in this determinant being 0 must be an eigenvalue. This is how we find the eigenvalues. We take the determinant of this matrix, set it equal to 0, find the resulting lambda values. And this determinant is just lambda minus 1 times lambda minus 2 minus negative 2 times negative 3. We see that there. This must equal 0. Doing some distribution and simplification, we get here, and then we can factor this polynomial as lambda minus 4 and lambda plus 1 set equal to 0. By the zero product property, then, we get these two eigenvalues. Lambda equals negative 1, which we already knew, and the additional second eigenvalue, lambda equals 4. So finding eigenvalues comes down to finding the lambda values satisfying the characteristic equation, which we see comes down to finding the roots of a polynomial. And this special polynomial that we use to find the eigenvalues is called the characteristic polynomial. So just like we saw in the previous example, if we expand this determinant in the characteristic equation, we end up with a polynomial like this. It's a degree n polynomial with 1 as a leading coefficient. Now, it's not completely trivial to see that this determinant does indeed lead to a polynomial of this form. I'll leave it to you to convince yourself that it does, and there's a link in the description to a video where we go over this in a bit more detail. For now, we'll just accept that yes, this determinant will lead to a degree n polynomial in lambda with 1 as its leading coefficient, and that polynomial is called the characteristic polynomial. So there is our characteristic polynomial of the n by n matrix A, and of course, since the eigenvalues are the roots of the polynomial, we know that there are at most n distinct eigenvalues, because a degree n polynomial has at most n distinct roots. Now, it's possible, of course, these are polynomials, it's possible that some of those eigenvalues are complex. For now, we'll mostly keep it real, but we will finish this video with a quick complex example because it's pretty interesting. All right, let's go ahead and do a 3x3 example. We're going to find all eigenvalues of this matrix, and then we're going to find some eigenvectors as well. So here's our matrix A, and we want to take the determinant of this matrix, which, again, remember, this just results from negating all the entries of A. So you see that, negative 1, positive 2, negative 1, and so on, and then add a lambda on the main diagonal. That's the determinant that we are interested in. This is a triangular matrix, so the determinant is very straightforward to calculate. It's just the product of the diagonal entries. So lambda minus 1 times lambda minus 1 multiplied by lambda minus 2. We now know the characteristic polynomial of this matrix. There is our characteristic polynomial, lambda minus 1 squared times lambda minus 2, and setting that equal to 0, we find these eigenvalues, 1, 1, and 2. So there are two distinct eigenvalues, 1 and 2. Now, if we're trying to find some eigenvectors, we could find eigenvectors corresponding to 1 or eigenvectors corresponding to 2. I'll show you how to find the eigenvectors of A corresponding to the eigenvalue 2, and you can find the eigenvectors corresponding to lambda equals 1 for some practice. Now, we know that if lambda equals 2 is an eigenvalue, well then AX must equal 2x for any eigenvector x. So the solutions to this equation are the eigenvectors corresponding to lambda equals 2, at least the non-zero solutions. Again, if lambda equals 2 is an eigenvalue, then the eigenvectors that we're looking for are the vectors that, when multiplied by A, in effect are just multiplied by 2. Now, multiplying x by 2 is the same as multiplying x by 2 times the identity, so we can subtract ax from both sides of this equation and then factor an x out. We're going to have 2i minus a times x equals 0, and any non-zero solution to this equation is going to be an eigenvector. So it leads to this matrix equation. This here is 2i minus a. You can verify that. We would have 2 minus 1 in the first entry. That's 1. In the next diagonal entry, we would have 2 minus 1, which again is 1. In the next diagonal entry, we would have 2 minus 2, which is 0. And the rest of these entries are just the negatives of a. So this times this equals the 0 vector. Now, what are the solutions to this system? Well, from row 2, we see that x2 must equal 4x3. So x3 is a free variable here because there's no leading entry in column 3. From row 1, we have that x1 must equal negative 2x2. So negative 2 4x3 then, plus x3. Negative 2 times 4x3 plus x3, that's the same as negative 8x3 plus x3, which is negative 7x3. Then we can describe all solutions parametrically by letting x3 equal t, and then the eigenvectors look like this. Negative 7t, that's x1, 4t, that's x2, and then t, which is x3. So any vector of this form, where t is not equal to 0, is an eigenvector of our matrix A, corresponding to the eigenvalue lambda equals 2. So these are vectors that, when multiplied by the matrix A, will actually just be doubled in magnitude. That's what makes them eigenvectors corresponding to this eigenvalue. Just to wrap some of this stuff up before our final example, these are some equivalent statements you could make to say that lambda is an eigenvalue of A. We could just say lambda is an eigenvalue of A. By definition, that's the same as saying lambda is a solution of the characteristic equation. That's also equivalent to saying that the system, lambda I minus A times x equals 0, has non-trivial solutions. If there's a non-trivial solution to this equation, then there's some eigenvector x satisfying this equation, and so whatever lambda is would have to be an eigenvalue. And that, of course, is equivalent to saying there is a non-zero vector x such that ax equals lambda x. This, pretty obviously, I think, is equivalent to that. You would just get things on separate sides of the equation. So all of these statements just mean that lambda's an eigenvalue of A. Some of them also have a little bit of eigenvector context, but they all just say lambda's an eigenvalue. All right, as promised, here is our final imaginary example. This matrix, you may recall from our discussion of matrix transformations, is the standard matrix corresponding to a 90-degree rotation. So what would that mean about the eigenvalues of this matrix? Well, as we've seen, if a matrix has an eigenvector, then multiplying that vector by the matrix just stretches or shrinks the vector by some scalar that we call the eigenvalue. But this matrix, by its very nature, does change a vector's direction, right? It's a 90-degree rotation, so any non-zero vector would surely have its direction changed by this matrix. So does that mean then that this matrix has no eigenvalues? Well, let's see. The relevant determinant is seen here. Again, it's just negating the entries of A and adding lambda on the diagonals. This is the determinant of a 2x2 matrix, so just multiply along one diagonal and subtract the product of the other, so lambda squared minus negative 1, so lambda squared plus 1. That would be our characteristic polynomial, and then we would set this equal to 0, and find that lambda squared equals negative 1. Hence, the eigenvalues are plus or minus the imaginary unit. So given what we know about eigenvectors and eigenvalues, we would expect this to either not work or be weird, right? Because this matrix, by its very nature, rotates vectors. So how could it be that there are vectors whose directions aren't changed when they're multiplied by this thing? Well, it turns out it does work, it's just weird. The eigenvalues are imaginary, and if you were to find the corresponding eigenvectors, you'd find those are imaginary also. Or more accurately, they are complex. So this leads to complex eigenvectors that somehow can be rotated 90 degrees without having their direction changed. Pretty wacky. And that is a thorough overview of eigenvalues, eigenvectors, characteristic equations, characteristic polynomials, and how to find all of this stuff. Let me know in the comments if you have any questions, and be sure to check out my Linear Algebra course and Linear Algebra exercises playlist in the description for more. If you find my Linear Algebra videos helpful, please consider supporting what I do by joining Wrath of Math as a channel member. You can get early and exclusive access to select videos, as well as access to my lecture notes at the Premium Plus tier. Thanks a lot for watching.
I'm the mathematical menace, the machinations of mankind. Two calculators at the same time, hand signs and abacus, finger count and calculus. I'm a V to the T, my parameter the rapidest. Happens like this, my lecture's the most prominent, dominant. Call me De Morgan, I get the compliments. The union in together like any time that we intersect, cause my opponents know they need